2. It says solve the following logs. Doesn't really tell us how to do it. All right, so we can use any method possible. And if I can use any method possible, I guess I'm going to divide by 2 on both sides. So let's divide by 2 on both sides. And I get the log of x equals 5/2. Yikes. What's the base there? 10. Or in other words, if I use Ben, 10 to the 5/2 power equals x. That's using Ben. And I don't know what that number is. Can somebody type that in there, Chuck?
316.228.
How much?
316.228.
228. Thank you, Gannon. So 316.228. So we're using the Ben rule again. So we've used a lot of different strategies. Log both sides, Ben it by changing an exponent, condense, expand. Ben it like Beckham. And the next one. I notice that it says natural log of stuff equals natural log of stuff. That tells me that my radical x plus 2 has to be equal to my x. Because if I have ln on both sides, then the stuff that comes after the ln has to be the same. Now what do I do? Square. So we square both sides. What is going on in this? So I square the left, square the right, I get x plus 2 equals x squared. Oh, look, it's a quadratic. Let's move the jump to the other side. 0 equals x squared minus x minus 2. You can use the quadratic formula, you can use a calculator, you can factor and then that means that my solutions would be 2 and negative 1. What should you always do when you're dealing with square roots and squares? Check your answers. Let me tell you why. Look on the right-hand side of the original. You guys see that ln x thing? If I stick in the negative 1, I'm doing the natural log of negative 1. Can't do that. So I know that this one doesn't work. And so really my only answer is the 2. So always go back and check your answers. That's just an example of why you should go back and check. And always check in the original equation that they gave you. Always check in the original. Letter C. I see 2 logs. Automatically, in my head, I think... What? Division. I think division. Or in other words, condense. Okay? So I change this when I condense it into just one logarithm because we know that subtraction, when we condense, changes into division. So I really have the log base 10 of the thing that comes after the minus is on the bottom. The thing that doesn't have a minus with it is on the top. And on the right side, I have a 1. Oh, if I change it to Ben, I see 10 to the first power equals x over x minus 3. Notice how kind of the nice thing about this when I change to Ben is that there are no more logarithms involved. Now you're involved in a, how do I get rid of this fraction that's on the bottom? Mason?
Times both sides by x minus 3.
Times both sides by x minus 3. So if I do that, I have 10 times x minus 3 on the left. When I multiply the right side by that, it just disappears. So I've multiplied both sides by the x minus 3. Or, you guys might remember it this way. What was this called when you did this thing? Yeah, your teacher probably taught you cross multiply. It's actually called the means extremes theorem. So that's what I just did. Cross multiply. On the left side, if I simplify that a little bit, I get 10x minus 30. And on the right side, I get just my x. And then I probably should move the x thing to the right side since all of my x's are over there anyways. So let me move my x's to the right. I get negative 30 equals negative 9x.
Yeah.
And then I would divide, of course, both sides by negative 9. And I get x equals 10 thirds. So you can write down 3 1/3. You can write down 3.3 repeating. You can't write down 39ths. That's not simplified. So I would take 3.3 repeating, or 3 1/3, or 10 thirds. Make sure you always have the simplified version. We're down to 3 problems. I don't know if I can get done with all 3 of them. Vroom, vroom. Let's talk about our calculator. I'm not going to do this with you, but I'm just going to tell you how to do it. In this one, whenever you see some crazy stuff and you're like, oh my goodness, I have no idea. Here's what you do. Stuff over here goes in y1. Stuff over here goes in y2. And then you do the second trace, 5, enter, enter, arrow, enter, and out pops the value of 3.776. So if you were actually graphing this thing, and you don't have to do this, I just want you to understand what was happening. One of them, the one on the left, this Y1 thing, was a graph that looked like this, and the other one, the one in the blue, was a parabola that it was opening upside down, and it looked like this. And what they're talking about is the value of where they're crossing, the x value of where they were crossing. So that's what we just found.
That's the question I was going to ask when you said you didn't have time for it.
Okay, well that's the answer that I have now that I don't have any time either. Again, this is recorded on the video. Application. How long would it take your money to double if you invested blah, blah, blah continuously? What I want you to see is that whenever they use the word continuously, that's when they're using this PERT equation that we learned about earlier in our unit. So, Sarah, give me an amount of money you'd like to invest if you had it.
$2.
In the thousands of dollars. 5,000. So the P is my investment. I invest $5,000. That means if I want to double my money, I'm going to get out $10,000 when I'm done. It doesn't matter what amount of money you start with. This will always work the same. And then you have E to the interest rate, which is 0.08, because they told me it was 8%, and T is the amount of time I have to invest for. So if you picked 1,000, this would be 2,000. If you picked $1, this would be $2. The funny thing is, in the end, when I divide both sides by whatever's in front of the E, I end up with
2.
2. Because 10,000 divided by 5,000 is 2. $2 divided by $1 is 2. $1 million divided by 500,000 is 2. So it's always going to turn out to be 2 when you're doubling. And then you get e to the 0.08t. Oh crap, my exponent is the variable. How do I get to that thing? Log it. So log both sides.
Lincoln Law.
And I get the natural log of 2 equals 0.08t. Why? Because we know that when we log an e, natural log an e that is, they're inverses and they cancel each other out. Oh, I need to get how many years this is going to be, so I divide both sides by 0.08. And when you divide both sides by 0.08, you should find out that it's roughly 8.66 years. So you can try that on your own later if you like. So the strategies are the same. Maybe try to get to the same basis. If you have something that has an exponent and an exponential, that's a variable, logs both sides. If it's an e, natural log both sides, so undo those. Is this our last one?
Yep.
Yeah! Oh! Sorry guys. This is this is the same kind of thing. Same problem as number 4. Give it a shot. We'll try it later. I'll try to record this right now so you can see it on the video.
Oh yeah.
All right, and number 5, very similar to number 4. You're investing $50,000. You're going to compound it, and you need to have at the end of your investment $350,000. And we know that we're going to do this thing continuously, so we're using this formula. So that's e to the RT, and we're looking for our rate, and we only have 30 years. So as you look at the things that are happening here, we see that our 350,000, that's how much we want in the end. We see that the amount of money we're investing is 50,000, and we see that our time that we have to invest is the 30 years. If I look to solve this thing, I'm going to divide both sides by 50,000, and I end up with 7 equals e to the 30r. Then to undo this, I natural log both sides. So I have the natural log of 7, natural log of e. And that means that I get the natural log of 7 is equal to 30 times my r. In order to solve that in the end, I'm going to divide both sides by whatever's in front of the r. So I divide by 30. And I get the natural log of 7 divided by that. So I end up with 6.49% as my interest rate. And this is the last problem that's very similar to the previous one. The big idea is whenever you see a variable in the exponent, you need to log both sides.